One of my favorite problems in physics, which has a lot of applications in engineering, is called the simple pendulum. So the physics of this problem is that you have a mass m connected by a rigid rod of length L to a pivot point, and then this mass can oscillate around the arc of a circle. So gravity is acting on this mass, so we have a gravitational force mg pointing down. If the rod makes an angle theta with the vertical, then we can resolve this force component mg through a triangle, where this angle here is the same as this angle, so this angle is theta, and then the force along the direction of the arc is given by mg sine theta. So sine is the opposite, which is along the direction of the arc, divided by the hypotenuse, which is mg. So the force is mg sine theta. What we want to do now is write Newton's second law. The idea then is to write Newton's law along the arc length. So F equals ma. So our ma here will be m s double dot, and that's the force along the arc, which will be here in the negative direction, so it will be minus mg sine theta. So we need to resolve s in terms of theta. So our s, the distance along the arc, is just L times theta, right? L, the length of the radius of this circle times the angle. So then we got s double dot, so our equation becomes m. S double dot is L theta double dot is equal to the force along the arc, which is then the negative of mg sine theta, so minus mg sine theta. That's Newton's equation for our simple pendulum. We can simplify this a little bit. We can put everything on the left. We can divide through by m times L, and then we get the equation theta double dot plus g over L sine theta is equal to 0. This is the most famous equation for the simple pendulum. To make this more general, we can consider what happens at small oscillations. More general meaning that it has more applicability to other problems in physics and engineering. We make what's called the small amplitude approximation. Small amplitude approximation. So we assume that this pendulum is just oscillating with small amplitude down at the bottom. We can write sine theta then as approximately the first term in the Taylor series, which everybody should know is just theta. So then we get the differential equation theta double dot plus g over L theta equals 0. This is the differential equation for oscillations. We need some initial conditions. So let's say that theta at t equals 0 is some initial amplitude, which is assumed to be small, so that we start the pendulum up here, say. Let's say it has no velocity, so theta dot of 0 equals 0. And then the solution of this equation will just be the cosine function. So then we end up with theta of t is equal to theta naught cosine. The second derivative of cosine will bring out two factors of the argument to get g over L. So inside the cosine, there should be a square root of g over L times t. Okay? And that would be the solution of this equation. This equation is an equation which generally is called the simple harmonic oscillator equation. It's usually written in a more general way. One would write that equation as theta double dot plus omega squared theta equal to 0. In our case, omega then is the square root of G over L, but this applies to many other systems where omega may mean something else. Omega is called the angular frequency of the oscillator, and the period is given by 2 pi over omega. So the motion repeats every integer value of the period. So let me summarize. We've considered the simple pendulum here, where gravity acts on a mass connected by a rigid rod to a pivot point. We've applied Newton's law. We've obtained the equation for the simple pendulum, theta double dot plus G over L sine theta equals 0. Through a small amplitude approximation, we could approximate sine theta by theta, and then we've obtained the general equation for a simple harmonic oscillator, theta double dot plus omega squared theta equals 0. That gives us the oscillation sine or cosine. In this initial conditions, we constructed a cosine function. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.